Okay, welcome for another session of Introduction to Machine Learning. Today's lecture will be an introductory one on a topic called reinforcement learning. Reinforcement learning. It's a different style of learning, different from supervised learning, different from unsupervised learning. It's a totally different style of solving a problem. And so a couple of things, some analogies I want to give you. First of all, I want to give you the intuition of what is reinforcement learning. If you're familiar with dogs and you have trained dogs, then you are somewhat familiar with unsupervised learning or reinforcement learning, where you reinforce the dog. You want the dog to perform some tricks, such as go fetch the ball, and when the dog goes and fetches the ball, you give it a small treat and says, "Ah, okay. If I go fetch the ball, I'm getting a treat as a reward." So the dog actually learns. Of course, if the dog just comes back without the ball, you don't give it the treat, and so that will be a negative type of reinforcement, or it's a positive type of reinforcement. So that's how the dog learns. It figures out what to do based on what the environment, in this case the one who's trying to teach the dog, is providing a feedback from the environment. So it's that kind of learning. Or another example, I want to show you this device. I just brought it out. We use it to clean our house, and I'll show you what it looks like. All right. Do you know what this is? Anyone want to type in?
It's a Roomba.
Yeah, it's a Roomba. It's a robot that goes about vacuuming our floor. And some of the I don't know if I have the latest model here, but one of the most advanced models, they say it's AI-based Roomba, and it has AI, right? Oh, somebody. Okay, we are getting into Roomba discussion. Yep, Roomba. Yeah, the Roomba, is the Roomba really useful? I find it useful. Yeah, it's I don't have to go around vacuuming, right? So it just it does it for me. But you got to kind of empty it. Some of the newer models apparently have an automatic emptying mechanism. When it gets filled up, it goes and empties itself into that, right? Yeah, somebody says it's good if you have pets. Yeah, that's what I heard. I don't have pets because I'm allergic to dogs and cats, but I like them. I like dogs and cats. All right then. So the reason I thought I'd show you a Roomba is it uses reinforcement learning. It figures out where to go. Of course, you let it loose. You don't feed to it a plan of the layout of the house, or where do you put your clothes on the floor or junk on the floor. You don't tell any of it. It figures it out, and it does it with some feedback. It's going around. It's got sensors on it. It bumps into things and says, "Oh, okay, I can't go here." And it learns a plan of the house. It even figures out, where are the stairs, so it shouldn't fall down the stairs, and all this type of thing. It learns. So, what kind of machine learning is it using? The answer to it is it's reinforcement learning. So, there's the motivation for reinforcement learning. And there are so many other examples. It has been a very popular method for some game playing also. Apparently, the game of Go, the Chinese game of Go, it requires a high level of intelligence to win in Go, and it has defeated the world champion. Not the robot, but reinforcement learning methods have been used there by trying out things as what works, what doesn't work, that kind of thing. It gets feedback, and it wins like that. And also things like video games that many of you, I'm sure, are familiar with video games. And if you want a computer to do well on video games, it has to try out trial and error and reinforcement, things like that. So lots of interesting applications. I believe your project that Mihir and Saugata have designed for you has got to do something with game playing, I think, right? At least in the past, we used to give Tom and Jerry game playing, right? Some version of it, I imagine, here is designed for you. Okay, so that is the topic today, reinforcement learning. So I have two lectures on that that I will be using today. One is uh, one is an overview of reinforcement learning, and the second one is a little bit more details into and ending up with a technique called Q learning. We're going to talk about that. All right, so let me bring up my slides on reinforcement learning. All right, I got that one. Now I'm going to share screen with the file open. And there it is. Okay, there we are. Reinforcement learning overview. Okay, so what is reinforcement learning? Okay, so the topics we're going to cover in what is reinforcement learning. We'll first talk about reinforcement learning as a topic in machine learning. So that's a high level view. Where does it fit in, in what, how much of machine learning is about reinforcement learning and so on. And what kind of tasks are performed by RL as reinforcement learning, tasks performed by reinforcement learning. And the learning mechanism, it learns what's called as a policy. Policy is a strange term. We haven't seen that before. It's about what to do in any given situation. When you run into a wall, what should I do, right? What should the robot do? And the last part is reinforcement learning connected to a deep neural net. So today, everything gets connected to a deep neural net. So I've already gone over this briefly before. So there are three types of machine learning tasks, roughly three. There are variants of this. Supervised learning, which is simply predictive, where given an input, we learn for each input what should be the output from examples like that. And then so we can, in the future, when you have given a new input, we can say, hey, I know how to do this. You produce the output like you have learned from the supervision that was given to you, given to the machine. Unsupervised learning is where we don't have such kind of labels going along, and we saw examples of k-means and autoencoders as examples of unsupervised learning, where we have a bunch of data with k-means. We figure out how many clusters of data exist, right, in the data. Or in the case of autoencoders, we could use it to learn some representations of the data. What's a good representation of the data on a complex manifold and so on. So that's unsupervised learning, where you only have input and there is no output. Reinforcement learning is a strange thing that here we have an agent like the Roomba, an agent that is going around the world, which is a house. So the agent is crawling around the environment, and it runs into things, or it finds smooth pathways. We can think of runs into things as punishments, and smooth pathways as, oh, I can keep going like this. And it means that's a reward. It can move around. So how can it learn so that in the future you let it go and it has learned something about the environment and performs appropriately, right? More generally, a robot learns to move around. You want to have a robot that is able to walk around the house or whatever, right? Hallways and things like that. And the method here, I guess I have some equations for each of these methods. For supervised learning, it is, we are minimizing a loss function, where we're using this loss function is the cross entropy. We find the weights W to multiply the input by, and then doing softmax or logistic regression as output. That's how supervised learning works. In unsupervised learning, we are doing uh, this type of stuff where we figure out some parameters theta and the parameters theta, and we find the probabilities associated with the x's with each of the thetas, and that is computed in this way, basically saying that the parameters are consist of the particular classes that each data belongs to, right? That the missing class label is found out from each of them. In the supervised learning, we had the class labels. Here we says we take the data and we figure out what is the class label for each of the data points that we have. Like here we have unsupervised data, and we have colored them with the clusters. So that's the kind of thing that's going on. In reinforcement learning, we have a policy which says a mapping from the state to an action. State means what situation does the robot find itself in? What situation does the Roomba find itself in? And what should it do? Should it turn left, right, or halt, or so on? That's an action. So it's a state to action mapping. The policy it learns. So for any given state, it knows what to do. And that is done by a policy written as a pi for policy, optimal policy for state S involves an arg over all policies pi of RSA, the reward for the state and the action. So in any given state, if it performs an action, there is a reward for it saying, yes, I found a free way here. So you get like the dog getting the treat is the reward. Plus, there's more to it than simply getting the treat for that action. It is gamma, it is some value is a weightage type of thing. V star is an optimal value of all the future actions. So this is looking into the future. What should be the present reward we're getting, but also we should look further into the future because there is some kind of a goal we're trying to satisfy. Goal maybe the Roomba is trying to get back to its charging station. So what all should it do looking forward to such an action? So this is some futuristic evaluation that we do a local action plus some global lookup also. So that kind of intriguing thing is what reinforcement learning is about. All right, so here are some pictures of the Roomba again. All right, I just looked it up. Roomba, a particular model called 9800, uses reinforcement learning. So here's the Roomba, here's the charging station for it. And when you turn it upside down, you see all kinds of sensors. There is a cliff sensor here. So if it comes to a stairwell in the house, it won't fall down the stairs. So it senses the cliff. And then object sensors, it sends out some beams and says, oh, okay, I'm running into a table here or running into a chair here and so on. There's a cliff sensor here also, right? There are two cliff sensors. So there are multiple cliff sensors. Oh, four of them, all right, cliff sensors. And then there are two object sensors. And then look at this thing. The Roomba keeps on going around and round and round like that. And then it takes off after a while and goes around here and is going around a sofa and goes around and it's over here. There's a table over here and so on. So the Roomba is doing all of this. This was an example I found. I went to one of their, I looked up Roomba. So they have a website where they will try to sell you a Roomba, and they were kind of showing a family with 6 rooms in their house, and this is the plan of the house. You don't necessarily feed it to it because there could be all kinds of furniture laid out in the room. And here is the room with the furniture, a couple of comfortable looking chairs here and a sofa here and a coffee table here and maybe a, I don't know, TV or a fireplace or something over here. And this Roomba like this, it goes all over the place. And here is a map which is actually created by the robot. On their website, they show you how this Roomba is going around the entire house and it's coloring different parts here. It says, okay, your house looks like this, which is pretty much what this plan It's telling you it has figured out what the layout is, and it's also figured out where are all the furniture or junk or whatever, right? So it has figured out all of this. So it's doing this. So there's the kind of thing that the Roomba does. Okay, there's the motivation. We're going to have some specialized terminology now. We're going to call this Roomba as an agent, right? It's a new word, agent, we say. And the agent is the actor who's dealing with the environment. In this case, the robot is dealing with the environment. And we refer to this house with the furniture and all that as the environment. So there's a Roomba is an actor in the environment. And it has got some sensor inputs coming in, but it also has other types of feedback. When it finds, okay, if, the sensor is telling you there's a cliff, that's a stairwell. So it says, so I can't go beyond. So it says stop or turn around. So there would be the action. The environment is telling you there is an action for the state, which is the stairwell. Or here it is running into a sofa and we say, okay, it's telling you don't go that way. And there could be a positive one, which is, okay, your battery is low. You need to start heading to the charging station, which might be somewhere, somewhere here. And so that is our goal. We are over here, we are cleaning over here. It says, oh, battery low, battery low. We need to find out the closest way to get to the charging station. Maybe it's going to come across here and find itself the best way to go there. So it needs to plan that part also, saying, how should I get there? Should I go around the whole thing or what, right? All of this is the kind of stuff. And so here we don't have a teacher telling the Roomba what is the floor plan. We don't give this floor plan as input. It should figure it out. And so it has to do it on its own. So it needs to get reinforcement from the environment as to what should be done, and it learns that. So that is the kind of learning we call as reinforcement learning. So what is the task of reinforcement learning? We call it as an autonomous agent. That's the Roomba must learn to perform a task by trial and error without any guidance from the human operator. Isn't that great? It has to learn on its own without my having to label things and say, in this situation, you must do that. I suppose you could have a supervised learning for a robot also saying, if you encounter this, then you must do this, that kind of a thing. Here we are saying you need to figure this out. Reinforcement learning is the problem of getting an agent to act in the world so as to maximize its reward. So it gets some rewards. I guess the robot may not be Roomba may not be such a great example for rewards. But let's say you do things and you get some nice rewards, and we say, that's what I should look for. Maybe like a dog. Agent is a dog. Consider teaching a dog. You cannot tell it what to do. You cannot tell the dog, I'm going to throw the ball, go and bring it back to me. But you can reward or punish it if it does the right or wrong thing. So that is something that you could do, and say if it does the right thing, you give it a treat. It has to figure out what it did that made it get the reward or punishment, which is known as the credit assignment problem. So the autonomous agent there is the dog, which is learning. So we don't program the dog, of course. The dog has a natural reinforcement learning built into it. That's what we're trying to get an agent to do, a computer agent to do that. Let's look at some simple example. A common scenario we use in reinforcement learning is called grid world. So this is like the house plan. Here's the grid world. The agent here is this a robot in this little square. And we make up a little game here and say, robot, you must go and reach the diamond, which is located here. That's your reward. And along the way, there are some cells here with burning fires. And if you go into them, you're going to have a punishment for it. So agent learns by trying all possible paths and choosing path which gives reward with the least amount of hurdles. So it has to try. It has to try going into the fire. Oh no, I shouldn't go into the fire. It learns that and it steps back. And it says, oh, there's an open path. I can go here and maybe go there. It says, that's no good. So trace back here, go here, and then try this out. That's bad. This one was not bad. And then you say, ah, got it. Okay. So it should try to learn this, and it should try and figure out by maybe multiple epochs, trying it again and again and again and seeing what is the best way to do it to reach this. So agents learns by trying all possible paths and choosing path which gives a reward with the least hurdles. Each right step will give the agent a reward, and each wrong step will subtract the reward. Right? So that's how it learns. Total reward is calculated, right? When it reaches the final reward, that's the diamond. Okay, so that's a grid. This is a grid in which it is moving around. That's one example. So here is a more general statement of reinforcement learning. You see, when you see a description of what is reinforcement learning, you'll see this diagram usually. It says agent. Agent is an algorithm basically. So that Roomba, which is here, that we're saying that it's got a chip in it, and that chip has an algorithm running here, and that is the agent here. It interacts with the environment, and uh, and there's a feedback loop between agent, which is a system, and its experience in the environment. So there's an environment which is described here by the plan of the house in which it is supposed to clean here. And so the agent at any moment, what should it do? When you turn the button on, when you press the on button, it has to do some action. It has an action which is maybe move forward. All right. And the environment gives it some feedback saying, oh, that's good. That's good. So, okay, that's a positive. So it gives a reward, positive reward. So its state, you can say, is it is in a different point in the house now, since it's moved a little bit. So there is an action it takes, and the environment gives it a reward. And also the agent gets to know the state it is in. Previously, it was in a certain state, which is the start state. Now it says you're in this new state here. So it's keeping track of its states here. So a mobile robot, you can think of this as a mobile robot, has actions move forward and turn. And its task is to learn a control strategy or policy for choosing actions that achieve its goals. So it has to have a strategy at any given situation. What should it do? What is the action it should take? And what is its goal? Maybe it's planning to go to some far end of the house or whatever. What should be the actions, sequence of actions it takes? For instance, goal of docking onto battery charger when battery is low. The Roomba you just saw does that. So when it finds, it's been running for about 45 minutes or an hour or what have you, it says, okay, the battery is low. So it says, I need to perform actions such as heading back to its base, right? So this is the kind of situation we're talking about. And we need to formulate it mathematically so we can have a learning algorithm that does this. So the learning task. An agent exists in an environment with a set of states S. What is the set of states? S would be in the grid world. It's all these possible locations it could be in. It can perform any of the set of actions A. Move left, move right, uh, move, uh, move up, move down, right? Like that. Performing action AT in state ST. We use these symbols. A for action, S for state, receives a reward RT. So if you move to the left or right in the particular grid world, it will get a reward, which is positive or negative. Agent's task is to learn the control policy pi S to A, state to action. In any given state, what action should it perform? That maximizes expected sum of rewards. It should not be just local reward, but it should also be a globally reward. The reward may not be very local that it can move. The reward is, I need to do a whole sequence of steps, such as going to fetch the diamond or going to the battery charger. So we now write maximize expected sum of the rewards with future rewards discounted exponentially. So there is a reward for moving to the left, let's say, or moving to the right. And then what is the possibilities from there, and moving to the left and right, you're going to get other rewards. So can we calculate the reward for this step? And can we calculate the reward for the next step and the next step? This is like somebody who's really smart in playing chess. He not only looks for the immediate reward for the move, but also is looking down saying, what could I do in the next step? So we have an agent here performs an action AT with the environment. It feeds back the new state, and it gives a reward. So the agent learns from this. So we're showing that now specifically. And now we have this diagram which says starting S0, you perform action A0, you get a reward R0, you go to state S1, you perform action A1. So these are all variables that take on the given legal set of actions that are possible. We would be using. They're just placeholder variables, A1, A2, so on. Goal is learn to choose actions that maximizes R0, gamma R1, gamma R2, etc., where gamma likes 0, 0, and 1. What it is saying is, so when we are in a particular state, we need to get maximize. Perform that action, it's going to give you the most reward in that state. But it also says, plus look ahead, and you will have a reward at the next stage also, and you want to make these two together maximum, but it is multiplied by a discount factor here, gamma between 0 and 1. So we don't take R1 with as much importance as R0, and we multiply it by 0.9, let's say, 0.9 of R1, saying it's a slightly discounted value. And the action after that, it's going to be gamma squared. If it is 0.9, this is going to become 0.81, like that, right? 9 times 9 is 81. So, so we are kind of looking at, maybe we have to look ahead all over and say, choose the action that's going to be best based on all of these. So the summary of terminology for reinforcement learning is that we have action A, it's a possible moves that the agent can take. State S, the current situation returned by the environment, right? So the environment is telling you you're in this state now. Maybe it'll tell you the GPS of the robot or something like that, state, or where it is in the grid world. Reward are immediate return sent back from the environment to evaluate the last action. So you just did this, you just bumped into me, so there's a punishment or a reward. Policy pi, strategy that agent employs to determine next action based on current state. And value V is expected long-term return with discount as opposed to short-term reward. So there's a short-term reward and there's a long-term value. So I guess in life also it's like that, right? There's a short-term reward. You like to eat that sweet, and wow, that really is great. But the long-term value maybe is not good for you, and so looking down the line, it might not be good for you, right? That kind of thing. Short-term and expected long-term return with discount as opposed to short. Short-term is the most important, but we're also taking into account what may be the long-term effect of that. Defining an environment. Okay, there is an OpenAI toolkit for reinforcement learning called GYM, right? So my guess is you're going to be doing your project on GYM. We define action space, possible actions of an agent, and observation space, possible states based on action state, based on action. So this is the A's and this is the S. This is the actions and the space, possible states, and then the state, current state of the environment. Okay, so observation space is actually the state you're going to move to for that, from that action, and state is the current state of the environment. So those are the terminology in GYM. We also define the following methods: init, initialize environment with default values. Step, accept an action, calculates and returns new state, reward, and done state after taking this action. Reset, clear all the variables in the environment and reset it to its initial state. and to render, provide output for better debugging or showcasing. Okay, so the name of the game is learning a control policy. So target action to be learned is a control policy pi s to a policy that the reason we show it like this as a policy is not just one value of state going to a value. So in this state, you must do this action. What about all the other states you could be in? So specifying all of that completely would be a policy that outputs action A given state S. So this is a set of all possible states. Determine as to what action to take in a particular situation so as to maximize cumulative reward, right? So we need to figure this out. The policy we need to figure out. Problem is one of learning to control a sequential process. It's a sequential process, one step after the other. In manufacturing optimization, right? So supposing we are manufacturing something, what sequence of manufacturing actions must be chosen? So let's say we want to produce a COVID vaccine, right? That's what people are talking about today, manufacturing the COVID vaccine. And so what sequence of manufacturing actions to be chosen? Reward to be maximized is value of goods produced minus cost, right? So what will be the final value of the goods produced? And of course, you're paying a price for doing that. So anyway, so a problem is one learning to control a sequential process. So could be used there also, I suppose, in manufacturing optimization. This slide is just again a throwback on how RL differs from other ML. We just saw that, but it's putting it in the terminology of reinforcement learning. So in reinforcement learning, there is a delayed reward. In other types of machine learning, training example is S comma A equal to pi of S. So we are told that for this state, this is the answer, which is a label, or it could be action. We could say, well, input a state and tell me what is the action for that. So that would be a supervised learning type of problem. In reinforcement learning, trainer provides an immediate reward for action. Which actions are to be credited for the outcome. So we are learning here what are the actions that are needed for the outcome, which is the overall goal. So exploration is another thing. Agent influences distribution. So in a sense, the data it is learning from is created by the agent. In the other problem, we had some data where we had the labels given to us. Here it says, you try it out. So there is an aspect of exploration. So the robot has to explore, saying, let me try this one. I have no idea what's going to happen. And then it'll learn from that by action sequence chosen. So which experimentation produces best learning? So what should be the kind of exploration it should do? Exploration of unknown states and actions. The other type of policy that it can do is exploitation. That is, if supposing it has learned some things, it knows that it can go straight ahead and doesn't run into any obstacles, then what it is doing is exploitation of states and actions already learned. So should it keep trying new things, or should it follow a safe method that it already knows about? So this is a classic problem called exploration versus exploitation, which occurs in several areas of machine learning, including this. Partially observable states. Entire state may not be observable, right? So all the states may not be observable. Need to combine previous observations with current sensor data when choosing actions. So it is some kind of a, finding its way, right? It's like not everything is right away known. All right, the slide says exploration and exploitation. Those are two different words. Reinforcement learning requires choosing between exploration and exploitation, right? Try this out, right? I suppose it's like going to a restaurant, an ethnic restaurant, and you have no idea about the kind of food there is. You might have heard of one or two items. You might order that saying, okay, I know that one. Um, but there is so many other items on the menu, and maybe some good stuff there. So you may want to try out some. So that would be exploration rather than exploitation. Exploitation refers to taking actions that come from the current best version of the learned policy, action that we know will achieve a high reward. Exploration refers to taking action specifically to obtain more training data. So in a way, we are regarding what is obtained in this process as training data. You can think about it as if you do this, I will learn something. What is the result of that? So in this, so you can say this action in this state gives me that kind of a result. So policy with exploration and exploitation. Given context C, action A gives us a reward of 1. We do not know if it is the best possible reward. We may want to exploit our current policy and continue taking action A to be sure of obtaining a reward 1. We keep on getting reward 1 if we take that action in this, because we have done this before. We may also want to explore trying action A prime. This is different action, move to the left or move to the right. We do not know what will happen if we try A prime. We hope to get a reward of 2. Okay, whoa. Instead of just settling for a reward of 1, if I move to the right, what if I get a reward of 2? That's great. But we run the risk of getting a reward of 0, right? So exploration can be risky, but you can get good rewards also. Either way, we get some knowledge saying if I go this way or that way, hey, that's great. And if it is 2, maybe in the future you will exploit that one always. But if you get a 0, it says, okay, never do that. So implementation of exploration, implemented in many ways, occasionally taking random actions intended to cover the entire range of possible actions. And so it could be randomly you can try this out, and or model-based approaches that compute a choice action based on its expected reward and the model's uncertainty about the reward. So we have some kind of a model that gives us an expected value, that somehow we are able to say, if we go here, we may get this kind of a reward. So preference for exploration or exploitation, factors for preference. If agent has only a short amount of time to accrue reward, then we prefer exploitation. So if we say, look, you must go reach that diamond in a very short number of steps, then we say, okay, we're not going to do too much of exploration. If agent has a long time to accrue reward, we begin with more exploration so that future actions can be planned more effectively with knowledge. As time progresses, we move towards more exploitation. All right, let's see, intuitions from other disciplines. Reinforcement learning, we're still talking about the overview of reinforcement learning rather than the nitty-gritty of it. Reinforcement learning has a very close relationship with psychology, biology, and neuroscience, right? A lot of AI is like that, isn't it? About analogies with the brain and all that. What a reinforcement learning agent does is just trial and error. It learns how good or bad its actions are based on the rewards it receives from the environment. This is how a human learns, let alone a dog. We also learn like this according to this, right? We try it out. Oh, that's fire. If you touch it, it burns. Okay, don't touch fire. So humans also learn like this, like a dog. And besides exploration, exploitation, and credit assignment, attempts to model the environment are also something we face in our everyday life. Attempts to model the environment are also something we face. I guess this is a very profound statement that uh, so we are trying to model the environment, saying what kinds of things are good, and I suppose older the people are, they've figured out, they've tried out this and that, and they know what works, and that's why they try to give advice to young people saying, I've been there, done that, so you don't do this. I guess the young people want to exploit or explore on their own and learn for themselves. All right, let's see applications of reinforcement learning. Use similar method for computers for game playing. So, like the programs for doing backgammon, chess, and Go. I mentioned Go earlier on. Scheduling jobs, robots in a maze, controlling robot limbs. I got an URL here. You may want to check it out. It's kind of fun to see this robot running around and runs into things and figures out and then does well. You can also have multiple agents. Not this is we just saw one Roomba is an agent. I suppose two Roombas running around the hall together would be multiple agents. Partial observability, all kinds of sub problems we can define. Reinforcement learning based on deep learning. So this is where you're bringing in the neural network with deep learning. Play Atari video games. DeepMind. There's a paper the people in this company called DeepMind. I believe it's a Microsoft company now. They play Atari video games, or maybe it's a Google company. It's a Google company, DeepMind. Robotics and reaching human level performance on many tasks. So this is a useful set of tools to have where this style of machine learning is more important. So what about data sets for reinforcement learning? Unlike supervised and unsupervised learning, reinforcement learning does not just experience a fixed data set. We don't say here is the data of the inputs and the labels. Reinforcement learning algorithms interact with an environment, and a particular style of learning called Q learning. We learn a queue for any given state. What is Q learning? In any given state of the environment, it knows what action to take, and it has already factored in the local reward in moving into that state, and it is also factored in the long-term goodness of that move, whether that leads to your ultimate objective. So that's called Q learning, and we'll see the definition of Q learning. Q learning generates data exclusively from experience without incorporation of prior knowledge. If we put all our history data into a table with state, action, reward, next state, and then sample from it, it should be able to train our agent that way without the data set. So it's also possible to have a data set where you move, you have all of this available, state, action, reward, next state, and sample from it. Saying, okay, so we know for any given situation, what should be the action and what state it will take you to. I have a few slides here. I don't know why I have them here. Application for reinforcement learning, resource management. Yeah, it can be used from some research management in computer jobs and things like that. So there are all kinds of applications. Robotics, robot learns policies to map raw video image to robot's actions. All right, so they have some applications there. Multitasking. Robot learning may involve learning several related tasks. Mobile robot may need to dock in its battery charger, navigate through narrow corridors, and how to pick up output from a laser printer. Right. This is kind of dated, right? Whoever uses a output from a laser printer, maybe we do occasionally, but very rarely. Reinforcement learning connected a deep neural net. Task is learning to navigate in a complex environment without prior knowledge. We just saw some examples of that. Reinforcement learning agent infers from complex environment. By punishment reward system, it can model decision making. Example applications are AlphaGo, Zero, beat the world champion, December 2017. OpenAI bought one Dota 2 World Championship, August 2018. I need to put some 2019, 2020 examples. Okay. All right. These last few slides here are about deep reinforcement learning for Atari breakout. This was a paper. This is already 7 years old now. Playing Atari with deep reinforcement learning. The paper was was a prestigious conference called NIPS. And so the code for it is all over here, and core libraries is OpenAI, Gym, Keras, RL, and all of this. And so they had some strategies, gives all kinds of little detail here. I'm going to skip that. And this is the kind of reinforcement learning of the Atari screen, where I suppose this game is about moving this cursor here, so that stuff coming from the top, you have to go and bounce it back or something like that. All right, so this is called Breakout in Atari, and so they came up with a program based on reinforcement learning of how to move this cursor around to be a good player of this Atari. All right, I just threw in that example. Okay, I wanted to say what are the actions, left, right? What are observations or image frame, this image itself? Reward equal to -100 if lose and -1 if win. And the policy P pi AS is all the actions for all the mappings from actions to states to actions. Q value, action state, and then Q. So these all have to be specified for this game. So typically, a particular reinforcement learning effort will have to specify all these kinds of things, and that's how you solve the problem. Okay. All right. So let's get into a little bit more detail if we have the time. Mihir, how are we doing on time? How much time can you give me?
We can go for 10 more minutes.
10 more minutes. Okay. I don't think I'll be able to cover fully um, all the definitions here. So what we now are going to do now is, is look into all the formal definitions now and of this Q learning I just mentioned earlier on. Okay, now before we move to this, were there some questions from my previous part of this lecture? All right, if not, we'll continue. The learning task. Okay, so that was an overview. It talked about what is reinforcement learning and how does it differ from supervised, unsupervised learning, and what are all the terminology of this whole new area, which we haven't seen before. And now we get into more specifically the definition of learning in this in such an environment with actions and environments, right? So the topics in the learning task are the reinforcement learning task. We now define what's called as a Markov decision process, or an MDP. So we're saying there's something Markovian about this, that we are in a state and we take an action when we move to another state. That might remind you of Markov processes. So where also there's a time dependency. We go from one state to another state. That's why this is called as a Markov process. It's a Markov decision process because we have to make a decision based on all the actions available to us and all the rewards. So that is why it's called a Markov decision process. And then we have this idea of a discounted cumulative reward. That is, the reward is highest for immediate action, and then there's a discount applied to future actions. And then we look at a simple example of a simple grid world. We just saw what a grid world was like. Now we'll be a little bit more formal about it and figure out how to specify all these things properly. So the learning task is to formulate the problem of learning sequential control strategies more precisely. There are many ways to do so. Agents' actions are deterministic or non-deterministic. Oh, okay. It's possible to have an action that is deterministic. That is, in this state, you always take this action. Or what about non-deterministic? Sometimes you have this action, sometimes you have another action. You choose one or the other non-deterministically, we say. We can't specify which one we'll do, but we'll do one of them. Agent can predict next state due to an action or it cannot. So these are all things we can specify. And so that's up to us to define the problem. Training by an expert may show optimal action sequences. So we may also have a training by an expert to show that's what you need to do. A general formulation is based on Markov decision processes. So formally, a Markov decision process, MDP, in such an MDP, an agent can perceive a set S of discrete states in its environment. So it can figure out where it is. Maybe the GPS will tell it where it is. Has a set A of actions that it can perform. Move left, move right. At each discrete time step T, the agent senses the current state ST, where it is on GPS, chooses a current action, and that's one of these actions that we know, and performs it, moves left. Environment responds by giving it a reward, RT equal to RSTAT. So it's the reward that from state ST, performing action ST, you get reward ST. And producing state ST plus 1, it has changed now its state. And that is given by this mapping delta of STAT. What is delta of STAT? Is it takes the state in action and results in a new state, and that is ST plus 1. And this delta is the mapping of performing action AT in state ST. So we have a delta is a function of STAT. R is also a function of it. So there's a reward and the next state. The function delta and R are part of the environment and not necessarily known to the target. So what is the state you're going to end up in and what is the reward you're going to get? Those are not necessarily known to the agent, right? Which we are maybe in the mode of exploration. So MDP dependency. In an MDP, the two functions, delta, which maps the current state to the next state, R, which provides the reward for the action, depend only on the current state and the action and not on earlier states and actions. So it only depends on the current one. We consider only a case where S and A are finite. There is a fixed set of states and fixed set of actions. We first consider the deterministic case for delta and R. So there is deterministic in the sense you are going to end up in state T plus 1 with that. It doesn't say it's a set of possibilities here. The reward also is fixed. So this is the example that we'll work out here. So let's say in this small grid world, we have G stands for the goal. And these are there are 6 grid squares here, represent 6 possible states for the agent. Only 6 here. Previous one we saw had more than that. Each arrow represents a possible action can take to move to another state. So we can move from state here to here by taking this arrow to the right. The number with each arrow is immediate reward RSA that the agent receives. So if you move from this state to this state, you get a reward of 0. That's how it's defined here. So if you move from the opposite way, this side to this way, you get a reward of 0. This is 0 this way, 0 this way, 0 this way, 0 this way. And again, if you're in this state, you go this way, get 0. If you come into this state, 0, 0. But look at this last one. It says, if you move into this final state, from this state here, you get a reward of 100. Oh, that's nice. Reward of 100. And if you're in this goal state, any action will result back in the goal state. You can't go to another state. You're finished. And if you're in this state over here, if you move up, you get a reward of 100. All right. So we now have specified in this small grid world environment, for every state and for every action, the action seems to be move left, move right, move up, move down. We have specified for every state the actions allowed actions and the reward that you get. And so the number with each arrow is immediate reward RSA agent receives. Gives reward 100 for actions entering the goal state in G and 0 otherwise. G is the goal state for which the only action available is to remain in that state. So now the question is, let's say we were out in this square here, and we say, what is the best way to go to the goal, right? If you don't know anything, you could go up here, or you could go this way. If you don't know anything, you could go up here, or you could go this way. So we went up here. Supposing we go back here, it's not really very good. So you kind of ending up. So it has to figure out the best way, maybe like this, like this, like that, or it could be like this, and like that, right? One of those. How to specify policy. Task of an agent is to learn a policy pi S to A for selecting its next action AT based on current observed state ST. And then how to specify the policy. One approach, required policy that produces greatest cumulative reward over time. For this, we need to define a cumulative value V pi ST of a policy pi, starting from an initial state ST as follows. V pi is the V stands for value, cumulative value of the policy pi you're going to use at state ST is equal to RT, the reward you get. And then we have RT plus 1, gamma squared like that. So generally stated in this way. Here, gamma is a constant that determines the relative value of delayed versus immediate rewards. Okay, I think this is explained a little bit better on the next slide, I think. Okay, discounted cumulative reward for policy pi is V pi of ST is this equation, which is equal to summation I equal to 0 to infinity of gamma to the power of I. Gamma is just a discount factor. If gamma equal to 0, only the reward, immediate reward is considered. So that would get rid of all these guys, just immediate reward. As we set gamma closer to 1, future rewards are given greater emphasis relative to the immediate reward, closer to closer. It's becoming, these are all important now. Future reward discounted with respect to immediate rewards, future rewards, all right? I just threw in some philosophical statement. There was a famous philosopher, economist, I believe, Keynes, right? Keynes. He said, in the long run, we are all dead. All right. How far do you look at in the long run? Do we do this for the short term, or should we look way ahead in life? If you do way ahead, Keynes says, in the long run, we are all dead. So I might as well do something for the short term, but not necessarily immediate short term. How about a finite horizon reward? Undiscounted sum of rewards or finite H steps. So you say, well, we don't look at it infinity, but we look at next 2 steps, next 3 steps, next 4 steps. Or the average reward over, this is summing all these rewards, 0 to H, limit H tends to infinity is the summation of this. It kind of amounts to the sum of all the rewards. And in the limit, as H tends to infinity, right? So there's no gamma in this case. There's a gamma over here. So, one can define all kinds of rewards that you are going to try and maximize. So the action that you're going to take will depend on the immediate reward. It also depends on an idea called long-term reward. It's called cumulative reward. So the agent has to learn a policy pi that maximizes V pi S for all states S. We just saw this example. And the best policy will call such a policy an optimal policy pi star among all policies. Pi star is argmax that it's going to maximize this quantity. So V pi of S for all S, for every state, that is. For every state, it gives you the best long-term reward as defined like this. So that's the policy. We define the value of V pi star S by V star of S. So that is the value long-term value. It gives the maximum discounted cumulative reward that the agent can obtain starting from state S. So let's see, an optimal policy. Once the states and immediate rewards are defined and we have chosen a value for gamma, we can determine the optimal policy pi star and its value v star of s. Let's see what this is. This was a previous diagram we had. We say that the values that are all shown over here are RSA values. That's the reward for a given state and a given action. So one optimal policy is if you're over here, go like this, go like that. If you're down below here, go like this, go like this, go like that. Or if you find yourself over here, go like that. It's like this, go like this. If you're over here, go like this. So it is specified for all possible states, the actions that are needed. And we say that this has specified the optimal policy. And how did you get this optimal policy? You say, hey, look over here. If you're over here, you know, we figured out going here and it was not as good as going to the right here, and you get a shorter path here and so on. And so the count of the path is shorter this way. So optimal policy is obtained by determining values of V star of S and QSA. We'll talk about what is Q. Q is actually the sum of the reward for the action plus the long-term reward V star. So optimal policy is obtained by determining the value of V star S and QSA. So we have to take into account the RSA and the V star for every cell. Together is what the Q value is. Selects one action agent with will select any given state. Optimal policy directs the agent along the shortest path towards the state G. And the value of V star for each state is shown. So we saw RSA earlier on. So what is the V star? It's kind of interesting now. We got some new numbers here, 90, 100, 0, 81, 90, 100. So value for each star, for bottom right state over here, value is 100 because the optimal policy in this state selects the move up action, right? If you are in this state, you look at it, what is the value you get if you're moving left and going up? It says, okay, going up is the best one in this, right from here. Going up is 100, and going to the left is 0. So this is better. All right, so we say the value for the bottom right, the value is 100. So this is the best value you get in this state is going from here to this according to the previous RSA value here. For bottom center state, how about this one? The value is 90. How did that? This is because the optimal policy will move the agent from this state to the right. All right. So if we are over here, the optimal policy will generate an, this is because to the right, generating an immediate reward of 0, then upward generating a reward of 100. Thus the discounted future reward is 0 plus gamma times 100 plus gamma squared 0. So it's equal to 90. So we say that this one, the value of this cell is the best value you have here is 90 for this cell. All right. So that is the looking ahead of moving here and then moving up here, right? So if you move here, you get 0, you get 100, but the 100 gets discounted by 0.9, which is why it's become 90. Gamma is equal to 0.9 over here. So we say this value here is 90, whereas this value here is 100. So the RSA values we just saw, the V star values we just saw, and the optimal policy is for each state, the policy we saw that it can be specified as to what the sequence should be. Now the QSA value are interesting. This is the Q values we say. The Q values is the values of the RSA values and the values of the V star S values, right? Q values, okay, Q values specify for every state and action, all right? So we say the Q value for each state transition is equal to the R value for the transition plus the V star for the resulting state discounted by gamma. I guess let's take a look at it over here. the QSA value is the R value going this way was 0, but the V star value is 90. So we say that's 90. And let's say for the bottom one here, it is 81 plus 0. What about going from here to here? So this is 0, and we have, I think a gamma is coming into play over here. Yeah, so there is 81 is 9 times 9 is 81, right? So there is 90, and this is uh, 72 over here. That's what I'm trying to figure out. That's the last slide. No. So the Q values for every state and action are shown. Q value for each state action transition is equal to the R value for this transition, which is this, plus the V star values for the resulting state discounted by gamma. So it is discounted by gamma, right? So we discount it. And of course, these 81s are good. The 72 is the only question I did. Okay, we need to take a closer look at it. And how do we justify the 72 value over here? Anyone have a quick answer to that? So which involves the discounted value, V star value, and the resulting state discounted by gamma. .72 sounds like it's 0.90 times 0.8, right? That would give us 72. 0.8. Are we going from 0.9 to 0.8? That's the question. It didn't sound like it. Okay. I'll send you an email on that. Let me think about it a bit more. Okay. All right. Meher, you want to take over now?
Yes, Professor.
All right, then. Do I need to make you the host or something?
Not really. It's fine.
Not really? Okay. So I can log out on this. All right, everyone. Have a nice, good Thanksgiving holiday. Don't have a class on Wednesday. And we'll be back in class again next Monday. Okay. So stay safe. I guess that's the most important thing. Coronavirus is pretty rampant all over in the US right now.
So the quiz 11 is available on UB Learns. If you have any questions regarding